Welcome to the second Matroid seminar. And let's go over the stuff that we did on last week, briefly. So a matroid is a set E of n elements and a family of subsets of E that satisfies three axioms. The first is, trivial. The second is also very straightforward. It was just the third one, and that Whitney recognized that matrices satisfy that third axiom. That was an amazing achievement. So members of I are called independent sets, and a subset of E that is not independent is called dependent. Minimal dependent set is called a circuit. There's a little bit of terminology clash with graph theory because circuit in a graph is something else. For us, the circuit and the cycle in a graph are the same. So matroid, the circuit, there are circuit axioms too. A matroid M is a set E of n elements and a family script C of subsets that satisfy these three properties, of which the first two again are straightforward. It's really the third axiom that is substantial. So these two axiom systems are equivalent. And showing the equivalence of these systems is a non-trivial task. In a beginning Matroid student can actually get really hung up on equivalence of the various axiomatic systems, and it's best to sort of bypass that and get on with the subject. So we did three examples on last Wednesday. Uniform matroids URN, that's the notation where R is less than or equal to N. And the independent sets are the sets of all subsets of size less than or equal to R. So by the definition of circuit, minimal dependent set, the sets of size R plus 1 are the circuit. And then vector matroid, this is another very large class of matroids where you take a matrix and row reduce as needed to be in this format and label the columns 1 to n. Then I is this independent sets of columns of the vector space V R, F. So it's vector space over the field F. F could be anything. And then C consists of the minimal dependent sets. And in our example, our first example over here, there were lots of independent sets, and these are the minimal dependent sets. So if the field is binary field, then it is called a binary matroid. And if the field is ternary, here we are, then it's a ternary matroid. And in general, if all of these matroids representable over various fields are called representable matroids. So if you take a graph as an example, and this was the one that we did, then we label the edges, just the edges. In Matroid theory, we don't look at vertices. And the cycles are 1, 7, 1, 2, 6, 4, 5, 4, etc. They are the same over here and listed above. So this is a graph representation of this. I'm sorry, this is, yeah, so this is this graph and this matrix. They're really the same object when viewed as a matroid. So, sort of the matroid is like the abstract set system object, and it can be represented by this matrix A, or it can be represented by this graph A. And that's where we were. So now let's do some more axioms. So we did minimal dependent set was a circuit. So now let's do maximal dependent set. A maximal independent set is called a basis. I may have said dependent by mistake, it's independent, okay? Maximal independent set is called a basis. And what does maximal mean in this context? It means B is independent and B union E is dependent for all E that's outside B. So that's what maximal means in this set. Our next proposition is essentially the basis axioms. Let E be a set and be the subset script B of E that are maximal independent, that is their basis. Then B satisfies the trivial axiom, it shouldn't be an empty set. And this one, this is called the basis exchange axiom. Then there exists F in B2 minus B1 such that B1 minus E union F is in B. So let's have a picture going here. So you have B1 and B2. Maybe they intersect, maybe they don't. So B1 is in, E is in B1 minus B2, F is in B2 minus B1, and then you can swap them out. B1 minus E union F. This is called the basis exchange. So we want to show that the maximal independent sets satisfy two. Right. So proof. One is obvious because the empty set is in I, therefore the empty set is also in B. So take two bases, B1 and B2 in B. First, we'll show that they have the same size. I actually have this, I do this proof in my linear algebra 1 class for matrices, and bases have the same size for all vector spaces, not just for Rn, so for abstract vector spaces too. So suppose not, that is B1 is strictly less than B2, then since B1 and B2 are both independent, the independence axiom 3, right, implies there is an E in B2 minus B1 such that B1 union E is also independent. That is, B1 can be grown by the independence axiom 3. So this is a contradiction to the maximality of B1. We said B1 is a maximal independent set. Therefore, B1 is greater than or equal to B2. And similarly, B2 is also greater than or equal to B1. Therefore, B1 equals B2. So the proof that I do in my linear algebra class is very different from this. We don't use axioms, I3 or anything, but this is the idea that every basis has the same size is just quite a fundamental thing. Okay, so continuing, let E be in B1 minus B2. I see that there are several more people I didn't notice. Feel free to stop me at any point. You're welcome to ask questions and stop me at any time, okay? So let E be in B1 minus B2. Then B1 minus E is strictly less than B2, right? So because we said that they're the same size, so if you take out an element, then it's going to be strictly less. So therefore there exists an F again by I3 in B2 minus B1 minus E such that B2 minus E union F is independent. So let B dash be the maximal independent set in I containing B2 minus E union F. By claim 1, B1 has to be equal to B2. Where are we? B2. I'm missing a subscript here. I have this should be B1. Yeah. Okay. B1, and that's B1. So B1 is equal to B1 minus E union F. And therefore, B1 minus E union F is some B dash, right? That is a basis. Yeah. Any questions? So that's why the basis exchange holds. So our goal was to prove that you can find an E in B1 minus B2. Our goal is to prove that given an E in B1 minus B2, there exists an F in B2 minus B1 such that you can swap out E and F. So here we showed that they have to have the same size, and then we have just a couple of lines here wrapping it up. Any questions? Should I go on? Okay, so then proposition 4 would be the independent axioms are equivalent to basis axioms. In this one, I won't do. One direction was the previous proposition. It's so the other direction is the harder one, and it just takes a long time to do. So I'll skip this proof. All right, so before we move on, and again, the basis axioms is this. The basis exchange, you can swap out one element with another and still get a basis. So B1 minus E union F is a basis. let's just quickly go over some graph theory. Like we also did some, we used some concepts of graph theory even last Wednesday, but they were, you know, I didn't go through it in detail, but this time I just kind of wrote it out in advance, just to do it carefully. So I think everybody knows this, so please bear with me as I repeat. A subgraph is a substructure, right? So you have G and it's your graph, and H is a subgraph if VH is a subset of VG and EH is a subset of EG. A spanning subgraph is a subgraph that has all the vertices, right? And two vertices are connected if there's a path between them. A graph is connected if there is a path between every pair of vertices. And the definition that I'm interested in is spanning tree. A tree is a graph that has no cycles and is connected. And a spanning tree is a spanning subgraph. Oh, there it is. That's my definition. A spanning tree is a spanning subgraph that is also a tree, right? So here, this is a spanning tree of G. This is also a spanning tree of G. And the basis exchange axiom is very easy to see in spanning trees. So if you have this as T1, this is T1. And this is my other spanning tree, T2. You can swap out E and F and get another spanning tree, T3. And then you have Kirchhoff's beautiful matrix tree theorem that tells you the number of spanning trees in a graph. And it would be great if we had the number of bases in a graph, but we don't. We don't have a nice formula for that. So let's look at our examples again quickly and going backwards. So in a graph.
When you say there's no nice formula for that, you mean there are theorems that say you can't, there are no algorithms that do certain things, or what do you exactly mean?
Kirchhoff's matrix tree theorem, I think it's like the determinant of the first minor is the number of spanning trees in a graph. And there's nothing like that for a matroid. And I think someone has proved that you can't get a polynomial time algorithm for bases of to determine the number of bases in a matroid. But I have to hedge that a little bit. I would have to double check that. Okay, there's no nice formula for the number of bases of matroid like there is for graphs. Yeah. So let's see. So if you so example 3 was graphs, right? So example 1 was uniform matroid. Example 2 was a vector matroid, and example 3 was graph. So the basis in a graph is the spanning trees. And we already said the cycles, the circuits are cycles. And this is what I meant earlier when I said a little bit of terminology clash here. Circuits from a matroid perspective are just the cycles. I wish they were just called cycles. The basis is a spanning tree, independent subsets are, how should we say it? Forests, acyclic forests or something. So all the subsets of spanning trees. And just E, of course, is the edge set. Edge set of graph. Another slight terminology issue in graph theory, it's like N is reserved for the number of elements, a number of vertices, right? And M is for the number of edges. And in matroids, it's exactly the backwards. So N is the number of edges in the graph, okay? So This is so this is it for graphs. And then example 2 again. So basis is the usual basis in a matrix. And independent sets we already saw in the usual independent sets, and the circuits were the minimal dependent sets. And example 1 again, URN, the uniform matroid on our elements. So we said I was the subset, independent sets are subsets of size less than or equal to R. B is subsets, the maximal ones, right, of size exactly equal to R. And C is subsets of size exactly R plus 1. Okay. So something very nice that that I like to do right up front is the fundamental circuit. All right, and you'll see as in like a few minutes why I want to do it. So let I be an independent set. And let E be something that's not an I, such that I union E is dependent. Then there exists a unique circuit in graph theory think cycle contained in I union E. There exists a unique circuit C contained in I union E, and such that E is in C, right? Just write it. This is clear, that E is in C is contained in I union E. Proof. Suppose C and C dash are distinct circuits contained in I union E, right? So you have your I, you have your E outside it, and you had sort of C and C dash, both containing E. And by the circuit elimination axiom, I have C2 here, so it's C2, I think. So then by, let me just see. So then by C2, the second axiom, C union C, no, C3, typo in my notes, C3. C union C dash minus E contains a circuit. But C union C dash minus E is entirely contained in I, which is independent. Contradiction. All right. So that's by the circuit elimination axiom. I guess when I wrote it, I just called them 1, 2, 3. So this is circuit axiom 3. It's convenient to call it C3. Okay, so there can be just one circuit like this. A couple of notes. We call this the fundamental circuit. If B is a basis and E is not in B, then this proposition 5 implies there exists a unique circuit C such that E is in C contained in B union E, and this is what we call the fundamental circuit. Of E with respect to B. And two, every circuit C is the fundamental circuit of some element E with respect to some basis B. So we're down in the weeds a little bit. We'll come up for some air in a moment. So let me just give a reason here. Since C is a circuit, C minus E is independent, let B be a maximal independent set containing C minus E. Now B union E is dependent and contains a unique circuit by proposition 5. This circuit must be C itself, since C is contained in B union E. Therefore, C is the fundamental circuit of E with respect to B. And this fundamental circuit, what's coming up next? Yeah. And this fundamental circuit, so for example, so if you have this graph and you're taking this as your basis, then this edge E here is the fundamental circuit with, this edge E, there's a circuit containing this edge E and the green edges. Okay, so the next thing, we're going to go on to the rank axioms. Let me stop and ask. I'm moving on to another axiom system. And in a moment, I have some nice stuff about Whitney's original paper. And any questions? Is it equivalent? Yeah, to state as the basis as given basis B1 and B2 with E and B1, then there exists a fundamental circuit that involves E and at least one element F in B2, but not B1. So I'm not sure I can answer that question. It's probably true within each axioms, within each of the major axiom systems, there's multiple variations, okay? So Hudson, that's a really good observation. We should look into it and confirm that, okay? First thing to see would be like in Oxley's book in the exercises, where he's got a whole bunch of variations of the basis axiom. Okay, let M be a matroid with ground set E. the function, by the way, changing gears completely, each of the axiom systems is it's almost like a complete switching gears, you know, thinking of something else. And the techniques involved in improving stuff from one of these perspectives is very different from the technique involved in proving from another axiom system. The function R from the power set of E to the natural numbers given by this. Rank of X is the size of the largest independent set in X. So we define independent set, and using independent set, we'll define the rank function and associate with every subset of the ground set, E, a number. And the number is defined in this manner: size of the largest independent set in X. So this is called the rank function. And the rank of the entire matroid is just the rank of the ground set. And this matches up with the rank in a matrix. So that notion of rank in a matrix is in just this. The rank of a graph would be the size of a spanning tree, which would be n-1. So if n is the number of edges, the vertices there. So first thing we'll do is, how are we doing on time? Yes. Let E be a set and R be the rank function. We're going to do the rank axioms. Then R satisfies 0 less than R of X less than size of X. 2, for every X in E, if Y is contained in X, then rank of Y is less than or equal to rank of X. And 3, this is what's known as submodular property. And if you go to Wikipedia and type submodular function, there's an entire field of study on submodular functions. And submodular functions have apparently enormous applications to machine learning and this and that. And the rank function of a matroid is a submodular function. And there's got to be a whole bunch of applications for somebody, you know, in matroids and submodular functions, if someone is an expert in both. Okay, so we'll follow the style of sort of half proofs that we've been doing for our cryptomorphic axiom systems. We're only doing like one direction, and then the other direction we leave and say, we'll, you know, it's there in James Oxley's book. So once again, you know, these rank axioms are equivalent to the previous basis axioms, the circuit axioms, the independent set axioms. And where, you know, proposition 7 is going to be that equivalence, but we only do one direction and leave it at that. It's the other direction that's harder, actually. So proof. So we want to prove that the function, the rank function we define like this, satisfies the 3 properties, and 1 and 2 are just straightforward. So I'll just sort of check those off like this. My Apple Pencil might die any moment, in which case I will have to charge it up for a few seconds, but it charges up quickly. So yeah. So we have to prove 3. let A be a basis of X intersection Y, right? This is 3, just highlighting it here, that the rank of X union Y is less than or equal to rank of X plus rank of Y minus rank of the intersection. And as I said, if you go to that Wikipedia on submodular functions, they have like a really nice way of saying this and making sense of it in English. But we're just going to stay with this sentence in yellow over here. So let A be a basis of X intersection Y. Then A is contained in X union Y and extends to a basis B such that A is contained in B is contained in X union Y. So let's have a picture going here. So this is our A over here. So A is a basis of X intersection Y. So A is contained in X union Y then, right? So it will extend, it's basically an independent set in X union Y. So by axiom 3, it will grow. So it can extend to a basis in X union Y and call that basis B. And what's B going to look like? Let B be equal to A union C union D as shown. And this would be, so it's going to be some part here and then some part here. This is C and this is D. Now, rank and also A, C, D are all independent. Now, rank of X union Y is size of B, right? Because B is the largest independent set in X union Y. B is a basis for X union Y, and that's equal to A plus C plus D, right? And this is, this of course is rank of X intersection Y. So rank of X is at least A plus C, the sizes of A plus C, and rank of Y is at least A plus B, right? Because, and I can write a little reason here, because A union C is independent, so the rank of X is going to be at least the size of A union C here, because A union B is independent. I think we're almost done. So what's rank of X union Y? That's rank of X intersection Y plus C plus D. And that's going to be less than rank of X intersection Y plus rank of X plus rank of Y. Yeah, that's it. So the fact that this is a submodular function is really cool. It's just, you know, completely different from the stuff that we've been doing so far. And these 3 form, so this would be, say, proposition 7. The rank axioms are equivalent to the basis axioms. Okay, keeping an eye on the clock. I tried to finish on time and not bore you too much. So this is Hasla Whitney, and he was actually at Princeton when he did this stuff, and it would be fair to say Matroids originated in New Jersey. And so he did this when he was very young. And this is the paper, 1935 paper on the abstract properties of linear independence. And he introduced the first thing over there, those are the rank axioms, I think. And his rank axioms are slightly different. So Hudson, when you suggested a slight variation of the basis exchange, the basis axiom, yeah, that's possible. Within each of these major axiom systems, there's many, many variations. And so his rank axioms are slightly different than the ones that we did in the one in chapter 1 of Oxley's book. And what he did was he starts out with the rank axioms. So he does the rank axioms, the independence axioms, and the circuit axioms. This is a substantial, a very nice paper that's still very readable. So,
for those interested in history, there's actually a whole biography of Hassler-Whitney that Keith Kendig wrote for the MAA book collection.
Oh, cool. And what's his name? Keith?
Keith Kendig, Kendig, I think it is. I forget the title of the book, but it's...
Oh, you got to look at it.
So he talks about not only his work on matroids, but on surfaces and embeddability theorems and other things.
Yeah, and all the graph theory stuff that he did in the 1930, 31 leading up to this. I think he considered himself a topologist.
So, I mean, the book treats the mathematics as well as having a lot of pictures of him and his family and so on. It's a rather nice book, I think.
Oh, okay, I definitely have to get it. Yeah, I didn't know about it, thanks. So in our first example, our 3 examples, when we had the uniform matroid, right? So rank of X is basically the size of X if X is less than or equal to R, right? Because every subset of size less than or equal to R is independent. And if it's greater than R, it's just R. The R being this R, yeah. And of course, rank of M is just R. In our second example, in matrices, right? So M is equal to M of A, where A is a matrix over F. Then rank of X is the dimension of the subspace spanned by columns in A labeled by set X in the vector space. And rank of M is just the size of a basis. So the language matches up with matrix language. And example 3 again. So here M is a graph and R of X is just the size of the spanning tree, right? In, let's see, in G, how should we say this? A G delete E of G minus X, or just as we say, G restricted. We use the word restricted to X. So when you're talking about, this is easier to say than this. And it's just basically the number of vertices minus 1. So I have very nice notes actually that I will put up with more details than what's here. So because this actually might be a little bit hard to read, so my notes that I'll post notes along each talk that's easier to read than this writing. I put some effort into writing neatly. How are we doing on time? Okay, we should wrap it up. And there's, yeah, so then the next thing is just, I have a lemma before the, actually I have a lemma before there's a lemma here. So I'll put this down as lemma 7. That's it's very nice. We may need to do it for something else. And then proposition 8, but we'll skip the lemma right now. And it will be in these notes when I post it. And then there's proposition 9, which we'll also skip. So X is independent if and only if rank of X is equal to the size of X. X is a basis if and only if rank of X is the rank of M, and X is a circuit if and only if X is not empty, and for every E in X, rank of X minus E is equal to rank of X. So in Matroid theory, we kind of use this notation instead of saying it more precisely like that. So X minus E is really X minus the element E. And I think we'll use some of these later on. So that's why I have it listed here, but the proof is fairly routine. So this is how independent set would be expressed in terms of rank, basis in terms of rank, and circuit in terms of rank. Oh yeah, so here's the lemma. I anticipated not being able to do the proof of lemma 7, and therefore I put all this down in this one too. Forgot that I saw this coming and wrote it out. Okay, so I should remove this. Should have followed the pattern here. There we go. So that's lemma 7. That's proposition 8. And this is proposition 9. Anticipated this, I wouldn't be able to finish it. So let's pull things together now. Yeah. All right. So this was the example of the graph that we did the other day. I'm going to draw this again. V1, V2, V3, V4, and V5, right? So let's label everything nicely. E1, E2, E3, E4, E5, and E6. So this graph has spanning tree E1, E2, E3, E4. That would be a spanning tree, right? So let's write the incidence matrix. So this is incidence matrix. So this is E1, E2, E3, E4, E5, E6. V1, V2, V3, V4, and V5. So E1 is 1, 1, 0, 0, 0. E2 will be 1, 0, 0. E5 is 1. This is just the incidence matrix, okay? So I can do elementary row operations, and in fact, if you do these operations in order, R2 minus R1, R3, after that R3 minus R2, R4 minus R3, R5 minus R4 in this order, what you get is this matrix 1, 0, 0, and this. All right. And this is, now what happens is if you have that row of zeros, right, which can just be removed. And that gives us the matrix that we had earlier, 1, 2, 3, 4, 0, 0, 1, 1. This is E1, E2, E3, E4, E5, E6. Now, we could do this every time we wanted to get what I would call the Matroid matrix, but we don't. This is cumbersome. It's actually much easier to think in terms of the fundamental circuits with respect to B. So you pick a spanning tree, and you'll call it E1, E2, E3, E4. So that's the spanning tree over there. So the fundamental circuits with respect to B are E1, E2, E3, E4, E5, right? That's the fundamental circuit of with E5. And then the fundamental circuit with E6 is this one here. So these are the fundamental circuits with respect to B, with respect to B. And once you have that, so you sort of fill in the E5 just using this idea of fundamental circuits. So this is a matrix over the binary field F2, right? So this is an identity matrix. So if you add up 1, 1, 1, 1 everywhere, you get 0. And that's how you fill in. You're kind of using fundamental circuits implicitly over there when you put a 1 for every row, right? For every row over here. So this is V1, V2, but we don't want to say that because like one row disappeared. So, so that's how we get it directly using the fundamental circuits. And then E6 forms a circuit.
Can you explain that again? I don't understand how the fundamental circuits generate this matrix.
Okay, sorry, I know I didn't do a very good job of that. So let's try this again. So so this is the fundamental circuit with respect to this basis, right? E1, E2, E3, E4, E5. So E4. So put a 1, right? So put a 1 everywhere. And that's what this column here is. Put a 1 for all the bases, all the edges in the spanning tree.
So you're relabeling the rows of this matrix with the edges at this time? Is that what you're saying?
Yes. That's a good point. So relabeling it like this: E1, E2, E3, E4. Very good. Very good. Thank you. I appreciate it. I should have said that. Yes. And then, so put a 1 for each of these entries. And when we're doing this one here, put a 1 for these entries. And that's where you get these 2 and a 0 for the others.
Okay, thank you.
Thank you. Thank you. I should have said E1, E2, E3, E4. Yes, we are relabeling. See, because the vertices sort of disappear from sight when we look at it as a matroid. So we could get this matroid matrix by row reducing and doing what I did over here like this, or we could just get it from the fundamental circuits, which is what we always do. We just go directly like that. Okay. So almost done. So we think of a graph on T vertices as an object that sits inside the complete graph KT, which has size T choose 2, right? So these are complete graphs from Wikipedia. They're polynomially large objects. A simple binary, and simple means no loops and parallel edges, a simple binary matroid is a substructure of the rank R binary projective geometry. The notation used is PGR minus 1, 2. So we're kind of making this transition to geometries. And then the next, I think the next section is on closure and flats, which is very geometric. So this is PG22. So it's convention to use R minus 1. So this would be PG22. And these columns, they're all possible columns of 0, 1 with no repetition of length 3. And then this is PG32. So this is all possible columns of zeros and ones with no repetition of length 4. This is PG42 and PG52. And the size of this geometry is 2 to the R minus 1. Binary matroids are exponentially large objects as compared to graphs, which are, polynomially large. But the amazing thing is that their behavior is almost, not almost, but very much like graphs. And then the PG22 is a Fano-matroid. And this is the geometric representation of the Fano-matroid. And these are not graphs, these are geometries. So we have to make that transition from what we were doing earlier to thinking of these in terms of geometries. And we only have nice pictures for PG, for rank 3 objects, and rank 4, we have some that we can imagine in space, but very limited. And rank 5 and higher, it's, we don't understand 4 dimensions well enough to visualize it, but we can work with it. So this is PG23, by the way, the ternary projective plane. So, all the substructures of that. And shortly after Hassler-Whitney, actually, he presented it, I think, a year earlier, but then Garrett Birkhoff right away said, well, we're talking about, this is just geometric lattices, so we have to get to that point. And Saunders MacLean said, well, this is projective geometry over here. So while matroids sort of started in 1935, it's actually much older because projective geometries, projective spaces is a much older subject. And we have to, and in the next meetings, we'll talk about that. And so this is sort of the big picture where you have graphs and binary matroids representable over finite field, and arbitrary matroids. It's a very large diagram, not drawn to scale. And I'm not sure what this is. This must have been something that we talked about when I did it last time. Okay, so, and yet, graphs being the smallest class doesn't mean that it's the simplest class. Matroids representable over finite fields behave so much like graphs. Okay, this is a good place to stop. I try to keep it within 1 hour. Any questions? I will post notes. I will actually post, I have notes written out separately from these. So I will post neater notes, and I should stop the recording.